Today we are diving into the world of quantum mechanics. Our journey revolves around a simulation, which is driven by a remarkable equation called Gross-Witkowski equation, or the GPE. Throughout our exploration, we will employ the finite difference method to intuiting the nonlinear equation. This nonlinear equation, the Gross-Witkowski equation, or GPE, is named after Eugene P. Gross and Lev Petrovich-Witkowski. The GPE equation basically describes quantum particles, especially in systems exhibiting the Bose-Einstein quantum states. So now let's understand the equation. In the equation, this psi represents the quantum state of a particle in both space and time, and the psi square gives us the probability of finding that particle at any specific position at a specific time. So the first term in the GPE equation enumerates the time evolution of the wave function. The second term is from the time-dependent Schrodinger equation. It is just the Laplacian of the wave function. And the third term, that is most important term, is the nonlinearity term introduced by Gauss and Witkowski. In the code, we are using the harmonic oscillator wave functions and the potential, which is in 1D or 2D or in 3D. For numerical integration and the time evolution of the wave function, we are using RK4 method. And finally, we are verifying at each time step the conservation of probability and the energy. This is the plot of the potential in 2 dimension. We can clearly see as we are using the harmonic oscillator potential, the plot is parabolic in nature. We are using 3 types of wave functions in our code. The first one is the ground state wave function of the harmonic oscillator. The second one is the first excited state. And the third is the superposition of both first ground state and the first excited state. And the dynamics is as expected, which is stationary for the ground state and the first excited state, whereas it is changing, the probability density is changing with respect to time for the superposed state. We all know in high performance computing, enhancing the computational speed is very crucial. So here we have parallelized our code using 3 different techniques, that is using multi-threading, MPI, and using KUPI, which is briefly explained in the latter slides. Then we have estimated the computational time in each method, and finally we have calculated our speed up, that is just by taking the ratio of CPU time and the GPU time.
Multi-threading is a parallel computing paradigm which is used for high-performance computing applications. For this project, we utilized multi-threading to increase the speed of an n-dimensional Schrodinger equation solver. The code, initially written in Python, sequential code, calculates the wave function given the initial conditions and the potential after time t. Now it does this by breaking that time t into distinct intervals, and then for each interval calculating the values of the wave function for different positions. Now it calculates the positions based on the grid size. A grid size is the number of positions we require to increase the accuracy. So the higher the grid size, the more accurate wave function we get, but that also increases the computation time. So we have to find the right balance of grid size versus time. This code, which was initially in sequence, which was sequentially written, was run and tested on IIT Kanpur's supercomputer Bernard. It was then converted into parallel code by tweaking the functions, and then all of that was again tested in IIT Kanpur's supercomputer Bernard. The results are as follows. Here we can see the sequential runtimes for 1 dimension, 2 dimension, and 3 dimension for various grid sizes, all in the power of 2. So as expected, we can see that the runtime increases as we increase the grid sizes and as we increase the dimensions, because as we increase dimensions, the grid sizes are raised to that dimension. So if a grid size is 64, that means there are 64 squared positions that it needs to calculate for in each time interval. And again, similarly for 3 dimensions, it's 64 cubed. And obviously the runtimes sometimes, for example, after 512, they reach uh, crazy amounts such as 20 minutes or 30 minutes, which become impractical for research purposes. So for this reason, we implement multi-threading. Now with multi-threading, we can see pretty decent speedups. Here is a chart for 2D speedups and grid sizes for various threads, and we can see speedups such as 2 times, 3 times, 4 times. Our best speedup is up to 6 times with 16 threads and a grid size of 2048, which is exceptional because it reduces our runtime by approximately a factor of 6. For example, it goes from almost 40% to almost 6 for almost 40 minutes to almost 6 or 7 minutes, which is a great help for conducting research. Now, a similar trend is seen in 3 dimensions. We can see speedups of 2 times, 3 times, and the best speedup we have is 512 and 16. Unfortunately, we were not able to calculate for higher grid sizes because the memory was exceeded for these grids because of the memory capacity available to us. Now, the speedups can be clearly seen if we plot a y versus log x graph, in which y is the time taken and x is the grid size in a logarithmic axis. We can clearly see that as we increase the grid sizes, the time increases, but as we implement multi-threading and increase the number of threads, the time decreases. And the time decreases pretty drastically as we increase the grid sizes, and the same trend can be seen in 3D. Now, the reason that we don't see a proportional amount time increase as we increase the threads is because of the time taken to share data between each thread. Sharing data is really a hardware limit which cannot be controlled from the software end, and this really is the bottleneck of why we cannot increase why we do not see a speed up of up to 16% or up to 16 times or 8 times for 8 threads or 16 threads.
In our IDC project, we are assigned to work on Gauss-Petavsky equation, which is a non-linear Schrodinger equation. It is solved for its wave function with the help of RK4 method. Sequential code gives us wave function while keeping the normalization and energy constant. In our sequential code, we have 10,000 iterations by choosing the total time to 10 seconds and interval of time to 0.01 seconds. We can change the grid size and the dimensions in the sequential code, which can increase the computational cost in sequential code while going under the loop for 10,000 iterations. So here we need the MPI. For testing purpose, we use only 5 iterations by reducing the total time from 10 seconds to 0.05 seconds. Code is run on Bernard of IIT Kanpur. Here is the run for sequential code in Bernard. This algorithm keeps the normalization as 1 and also keeping the energy as constant. By increasing the dimensions and grid size, we can see here the total time taken by the code is increasing. For 512 number of grids and choosing the 3D dimensions, we can see the total time goes up to 7 minutes. And if we are going to run for 1024 grid size by keeping the dimension as 3D, then here the number comes around 56 minutes. All the numbers here provided is in milliseconds. As we seen in our previous slide, the runtime goes up to 7 minutes. So to reduce it, the whole code is converted into message passing interface MPI for the general number of ranks. We provided here the comparison of MPI run for different number of ranks with the sequential run. This is only for the 2D, 2 dimensions. If we consider the grid size as 256, dimension is 2D, and taking the rank as 16, the speed up goes up to 5 times from the normal sequential code. Similarly, if we consider the grid size as 512, by taking the dimension as 2D and rank as 8, we can see here the speed up goes up to 3.3 times. The whole code is just for the number of 5 iterations. Similarly, here is the comparison of MPI run for different number of ranks with the sequential code for the dimensions 3D. So if here we consider the grid size at 64 and the dimension is 3D, by keeping the rank as 16, the speed up goes up to 2.6 times from the sequential code. Similarly, if we consider the grid size as 256, by keeping the dimension as 3D, for rank 8, the speed up goes up to 2.5 times from the sequential code. Here the graph is provided to visualize the comparison of two-dimension run. The x-axis have the grid size and the y-axis have the time in seconds. This violet line is for the sequential code and others is for the different ranks. So here we can clearly see that the ranks are taking less time than the normal sequential runtime. And also by increasing the rank, the time reduces here. Similarly, the graph is provided for the comparison of 3 dimension. Here also we took the grid size as our x-axis and for the y-axis the time in seconds. So here we can also see that the ranks are taking less time than the sequential run, and also by increasing the rank, the total time taken by the code is also decreases.
Here we are using a library from Python that is similar to NumPy for our parallelization. This is KuPy library. So the difference between this NumPy and KuPy is NumPy uses CPU, whereas KuPy uses GPU hardware. We ran our code both in CPU and GPU by using the NumPy library and KuPy library respectively. And you can see the CPU time is in seconds, but the GPU time is in milliseconds order, tens of milliseconds order. And the point here to notice is the speed up. You can see for 1024 gate size, the speed up is less than 100x. But when we increase our grid size, we are getting 100x speed up. So the reason can be the reduction in the overheads. So what is overhead? Now overhead is related to the data transfer and this kernel launch, which takes a small fraction of the overall computation time. And that impact of these overheads on the total execution time gets almost negligible when we are using a higher grid size. This is the log plot of grid size versus computational time. So here we can clearly see the computation time using this NumPy libraries of the order of 10 to the power 5 for, we can see for example 8192 squared grid size, but it suddenly decreases to the order of 10 to the power 3 when we use this KuPy library. We have also calculated the times for CPU and both GPU in three-dimensional case. The grid size is in 3D. That means it is 64Q, 128Q, and 256Q. And we can clearly see the trend is similar to the two-dimensional case. So the reason is the same. That is for 64 it is worst, and when we just switch to 128, it is coming around 100x, and for 256 similarly it is increased, and that is 128.6x. This is the log plot of read size versus computation time for 3D case, and we can clearly see in this graph too the speed is 100x, around 100x for 128 cube and this 256 cube size.
Thank you.